Okay, so today's video is going to be about quantum entanglement. So we know about quantum entanglement as before starting about quantum entanglement, let's talk about particles as of individual, not as entanglement is correlation between two particles. So first we'll talk about the particles individually. Let's suppose if this is particle 1 and this is particle 2. Okay, now if this particle over here has a certain state, okay, and this particle over here has a certain state, and we do measurement, okay, and measurement could be observation. We are making some observation, okay, we are looking at this particle 1, okay. Now when we are looking at this particle 1, the state before okay, when a particle is not observed, it has a property that it is in a multiple, it's in a multi-state, multiple state of different probabilities, okay, probabilities. Then according to that, when an observation is made, we are making a measurement. What made that measurement did actually was it made the state, the superposition break, the wave function, or let me just use the symbol wave function, it collapsed, okay. When it collapsed, we got a definite state, definite state, okay. What was this definite state? From all the multiple states of the superposition, one state was measured and one state was found in it, which was, let's suppose, state A. This was a state which was measured, and same goes for this particle over here. Again, a measurement could be done on this particle too, and we would get a certain other state of this particle, which is, let's suppose, state B. Now talking about the states, state of particle 1 and state of particle 2, we did measurement differently on these two particles and we got different values. Even though we would have done different same measurements, they wouldn't depend on each other. They will not depend on each other. They're not dependent. Measuring particle 1 will not influence particle 2 as they are non-correlated correlated particles, okay, meaning measurements being made on both particles will not affect each other, while when we talk about quantum entanglement, what happens on that is the two particles have a mysterious connection between them, and I will say this is s is distance, unlimited, there's no range, no range. Applicable, I mean maybe I'm using label words, applicable to all distance. Okay, so the weird connection, or that's how Einstein described it, as mysterious or spooky. It's a weird thing. So what we say is this relation over here, this correlation, this line is nothing but showing, it's showing a correlation between these two. Okay, so what actually is happening here is this these two particles, particle 1 and particle 2, right now their their states depend on each other. Okay, meaning an observation on particle 1. Let's suppose a particle 1 has, we make an observation, we get state 1. Same time particle 2 will be affected. We will get a state for particle 2 as well, state let's suppose 2. So as a correlation, as correlated, what we will write is state of this particle plus state of the other particle. This plus sign over here is showing the correlation, showing connection. Sorry for the bad wordings. This connection. So let me make one improvement over here. In this one, the states will be written separately. This is one state, this is a separate state. There is nothing in between. So we have no connection. But here this plus sign is showing a correlation. Okay. And about these over here, A and B, it doesn't look like an A. They are the like the factors, the probabilities, or we could say the constants which play a major role in the states. Okay, they have a, because how do I define this? Like, let's suppose, let me give you an example. If we have two particles, particle 1 and particle 2, okay, and we have the state, okay, we know that particles spin and they have directions. Okay, So let's suppose same goes for this one as well. So let's suppose we do an example. Okay, we do an example. If particle 1 has state particle 1 plus particle 2, and so we have a state up, plus, down, so this is one example. So this is particle 1 and this is particle 2. Particle 1, sorry, if this particle over here, particle 1, is found to be alpha up and down, then connection made will show particle 2 to be down and vertical. Okay, so if someone will ask what's the probability of particle 1 to be, okay, what's the probability of particle 1 to be this, sorry, not this, up and horizontal. So what we will write is we will take a norm square of the constant in front of, or not front, at the like the front, the very first value of the state. So this will give us the probability of particle 1 to be up and horizontal, the state to spin to be up and horizontal. And same goes for probability for 2, for particle 2. Instead of going for particle 2 1, we'll just write particle 2 and we just write the state. Now, one important thing, the probability sum should be 1. Okay, and the length of the states should also be 1. Length of states should be 1, because in quantum mechanics we tend to take every, like in quantum mechanics we tend to take everything to be sum of 1. And since it's all about probabilities, we need a certain combination and that combination should equal to 1. That's why I said in a start that the multiple state of different probabilities, the states might be different, but they, and once it's broken, it will only have one single state of certain probability. Superposition. Okay, these are of particle. Now let's suppose this is just a rough example. 3 by 2, 1 by 3, 4 by 3. Okay. Now the 4 by 3 will be more than 1. I tried. If I'm right, it's more than 1. I just take values I know. 1 by 2, 1 by 4, 1 by 5. Now when sorry when observed, we get a definite value which is either of the above. Okay, either this or this. Others will vanish. We will only have one single value. And what else? We could also factor the states. Okay, we could factor the states as well. Sorry. And by factoring, we could also check whether the state is correlated or non-correlated. Okay, down and up. Alright, if I ask you a question that what's the probability of particle being in up and it being vertical, so it would be of course 0, as particle 1 has the property to be up and vice versa, the other one has vertical. So how I would say is, if okay, now this is yeah, okay, if let's imagine I find particle 1 and particle 2 to have certain states. The state which we have over here should be different. It will be different and measurements will be made to this. Okay, both will have states as there is a correlation. Yeah. So entanglement is a mysterious behavior of particles to be somehow linked with each other in such a way that the measurements will affect one another regardless of the distance which they are in. Okay, and so yeah, that's it. Thank you.